Alright, in this video we're going to talk about t-distributions, which I'm hoping will be a fairly easy concept because t-distributions don't really present any new techniques that you haven't already learned. What a t-distribution is it's sort of a more conservative estimate of a standard normal distribution, i.e., a z-table. They're a more conservative estimate because you don't have as much information to go off of, so you have to use this more conservative estimate for things like confidence intervals. Don't worry if that doesn't make a lot of sense yet, but let's take an example to sort of illustrate this point and use of a t-distribution. This will also serve, I hope, to provide a little bit of a refresher about concepts like confidence intervals. So, in our problem, let's say we're a marketing firm and we want to estimate the average household income in an American city. And so we start with, we take a sample of 20 households in that city. So we have an N of 20. And we estimate in our sample the average, we get an average income from that sample of $71,000. That's the household income that we get from the average of those 20 families that we surveyed. And let's see, we want to get a confidence, we want a 95% confidence interval. In other words, we want to be able to estimate a range for that the population, in other words, the overall household income for that city with 95% confidence. So, just to illustrate this, this is our range of possible actual population household incomes, and we have this x bar, meaning this is the estimate we got from our sample of 71,000. And we're looking for a range such that everything inside of it, all of this, is going to be 95%. This could have been more elegantly drawn, but bear with me. And everything out here, all the blue area, is going to be a total of 5%. That's sort of our uncertainty that we're willing to put up with, which means that individually, in this blue area, it's going to be 2.5%, and same with the blue area on the left. So that's our uncertainty. And so what do we have to do to figure out this confidence interval? Well, we can use an equation. It's sort of a variation on the standard equation we always use when we're doing sampling, and that is, so this time we're going to say, okay, well, I don't actually want to be in blue anymore. We're going to say x bar, which is the average that we got from our sample, plus or minus z, and here, okay, so because we're dealing with the 95% confidence interval, our alpha, this is the uncertainty, our total uncertainty is our alpha. But because this is a confidence interval, we're dealing with two sides, and so our alpha is split up. So we're actually going to say our alpha divided by 2, because that's half of our uncertainty. So we're looking for a z value here such that we're going to only end up with 2.5 to the right of it. Same thing over here. And in this case, our alpha is 5%, so our alpha divided by 2 is going to be 2.5% times our standard deviation divided by the square root of n, which is our standard equation. And a lot of this information we have. I mean, we've got our x bar, so that's 71,000. We can look up z, the z value that corresponds to 2.5%. Let's go ahead and do that now. So here's our z table. We're looking for 2.5%, so that's 0.025. Here it is. At z equals negative 1.96, we should get, of course, 97. We should get 0.975 at z equals positive 1.96, since this whole thing is symmetrical. And indeed we do. Okay, so we could really use either one of these z values. I'm just going to go ahead and use 1.96. Oh, but hold on, we don't actually have a standard deviation. We need a standard deviation in order to be able to use this, but one was not given to us in the problem. So I'm going to go ahead and say, what if, let's just assume actually we knew what the standard deviation for the population was. What if we said we know the standard deviation is actually $2,000. This is the standard deviation for the for household income, for average household income, sorry, in the city that we're interested in. So I'm going to plug that in. $2,000 divided by square root of 20, or n is 20, of course. That was our sample size. All right, so now that we've got all this information, we can go ahead and do some math, and working this out, we should come up with two values. When we subtract this over here, we should get 70,123.5 approximately. And the upper bound of our range should be 71,876.5. So that's 71,123, and this here is 71,876. These are both 0.5, sorry. Okay, so that is our confidence interval given this problem. So we can say, you know, based on our sample, we expect that the average household income for the city is somewhere between, for the entire population of households in the city, is somewhere between 70,123.5 and 71,876.5, and we're 95% confident that that is the correct range. In other words, you know, 2.5% chance it's going to be higher than 71,876.5, 2.5% chance it's lower than 70,123.5. Now, this is not a very realistic example, to say the least. And why is it not realistic? Well, it's not realistic because why on earth would you know the standard deviation for the population if you didn't know the population average? That just doesn't make any sense, right? I mean, if you have this measurement, you probably have the overall population average. Much more likely is that you don't have this at all. Is that you don't know the average for the population and you don't know the standard deviation for the population, and you have to figure out both using the sample. So what can you do? Well, if you don't know the population standard deviation, then you can actually use the standard deviation you got in your sample. And that's okay. That's perfectly acceptable. However, it means you're taking you're making an even bigger estimate in terms of, you know, so when you say your confidence interval, well, you had to, you know, you got this average from your sample, but you're also using your sample standard deviation, which, you know, that's a little bit, they're both estimates. So you can't be quite as confident because you've made two estimates now. So what you do is you use a curve that's not quite, that's a little bit flatter, it's a little bit more spread out than the standard normal curve. And so that helps you, that ends up giving you a wider confidence interval, meaning you're sort of, you're less, well, you might be 95% as confident, but it's for a bigger range. So that's how a T curve works, the T distribution works. And I want to show you what this might look like in practice. The thing about the T distribution is it's not just one curve. It's several curves, and they're more or less accurate depending on the size of your sample. So for very, very big samples, you know, it's going to look pretty much exactly like the normal curve. And for very, very small samples, it's going to be really spread out, giving you sort of an inaccurate estimate. So let me see if I can draw a few of these. Let's say this is our standard normal curve, right? This is what gives us z values. And I'm going to extend this a little bit on either side. The curves for our T distribution are going to be a little bit less accurate. You can see they don't go up as high. They're a little bit more spread out. Now this is getting a little bit extreme, but a little bit sloppy too. The idea here is that, so if this green, I can barely even call that a curve, but you know what I was going for here. The green curve would represent a very small sample size. So you've got this sample size and you've estimated an average, and you're also estimating the standard deviation from that sample. But it's such a small sample size, you're really not very sure about either one. Whereas with a very large sample size, actually the values that the t-table will give you are going to be almost exactly the same as your z-table would give you, meaning the curves are basically the same. So really anything sort of bigger than 100 in most cases, and certainly as you get up to sample sizes of 1,000 or several thousand, they're basically going to be identical. If you use the z-table interchangeably with the t-table, it ain't going to make any difference at all, pretty much. So, but in general, because you're estimating the standard deviation, you're being more conservative, and that's what the t-tables represent, is a more conservative estimate. We also use a different notation. When we talk about the standard deviation of the population, we use this symbol here. But when we're talking about the standard deviation of the sample, we use S. And so let's actually let's recalculate this problem using, and by the way, we use the same equation. So I mean, when our general equation, which we manipulate depending on the circumstances, for doing sampling is, for a sample, this would be square root of n. This looks like that. For the t distribution, same thing. Except instead of the standard deviation from the population, we're using S, and we still divide by the square root of n. It's the only difference. It's really nothing too fancy. I actually want to show you quickly. Oh, okay. There's one other thing. As I said, the larger the sample size, the more the t distribution tends to resemble the z distribution, or the normal curve, I should say. And the smaller the sample size, the more it gets kind of spread out. Well, we have this thing called degrees of freedom. And degrees of freedom are just defined as n minus 1. Your sample size minus 1. And the degrees of freedom that you're dealing with allows you to determine sort of the t distribution that you're using, how conservative or not to be with your estimates. So let's take a look at the t-table. One of the sort of trickier things about using, because by and large, everything I've said thus far should just tell you one thing, which is that if you don't have the standard deviation from the population, you should use the t-table instead of the z-table. It's really that simple, and you're going to be using, because you're going to have to estimate the standard deviation from your sample instead of from the population, because that hasn't been given to you. So using the t-table is a little bit funny. It doesn't work exactly like the z-table. That's because, now, by the way, you can calculate either a z value or a t value in Excel very easily, but I want to show you how to use the tables. You have to calculate for the degrees of freedom, and so we have a different looking table. The degrees of freedom appear down on the left side. Remember, this is just n minus 1. And along the top, along the top what you have is your alpha. Meaning, let me just draw this really quick. The top values represent these, everything to the right, sort of our probability to the right of a certain value, a certain number of standard deviations. And so that's what you're getting along the top, is the alpha. Everything to the right of a certain number of standard deviations. And the standard deviations themselves are given within the middle part of the table. So these represent standard deviations and a corresponding number of degrees of freedom. And then along the top, we get a certain alpha. So that sort of everything to the right of that number of standard deviations, the probability of appearing to the right of that number of standard deviations, or greater than that number of standard deviations. All right, so let's go back and work through this problem that we started out with But instead of using the standard deviations for the population, which isn't really realistic, why would we have that? Let's say we had to estimate the standard deviation from the sample instead of having it from the population. Okay, so a lot of this stuff stays the same. I'm going to go ahead and erase some of the things that we wrote down previously. Actually, I'm not going to do that. I'm going to open up a new page. All right, so we still have a lot of the same information. Let's see if I can remember it. We have an estimate from the sample of an average from the sample of 71,000. We have a sample size of 20. And that gives us degrees of freedom of 19. And we want a 95% confidence interval. And let's say instead of being given the standard deviation from the population, we have to use the standard deviation from our sample. And let's just say the sample standard deviation equals 2,000. That was what we measured in the sample. Forget what I gave you before. This is when we took those 20 values, they had an average of 71,000 and a standard deviation of 2,000. That came from our sample itself. So we're still going to use a very similar equation. We're going to say x bar for our confidence interval plus or minus t, and this is a little bit tricky. We say, okay, our t value we're dealing with 95% confidence interval, but again, that's going to give us an alpha of 0.025 and 19 degrees of freedom. Right? Multiplied times sample standard deviation divided by the square root of n. This is going to give us our confidence interval. So, okay, fill this out again, 71,000 plus or minus. We have to use our t-table to look up, okay, we're dealing with 0.25, right? That's our alpha divided by 2. We're looking for a curve such that, or we're looking for a number of standard deviations such that everything over here, I should have used another color, is 0.025. Because, this is a confidence interval, and same value over here, we're going to get 0.025. We're looking for the number of standard deviations here, but we're saying this is a t-curve. This is a t-distribution, not the standard normal curve. So let's find that. 0.025, and we have a certain number of degrees of freedom. Our sample size was 20, so our degrees of freedom was 19. And remember, I'm in the 0.025 column. And what I get is 2.093. So I'm going to write that down. Times standard deviation from our sample was 2,000 divided by square root of 20. And this gives us a range between 70,000, 0.64, and 71,936. All right, so that is our 95% confidence interval when the standard deviation of the population wasn't given to us and we had to estimate using the standard deviation from the sample. Notice something real quick. This range here, 70,064 to 71,936, is actually wider, slightly. It's not hugely, but it is slightly wider than the range we got when we used the normal distribution. And that's because the t distribution is more conservative because we had to estimate the standard deviation. So we would expect this. We would expect to see when we used the t distribution and the t tables, we would see a wider range in that 95% confidence interval. So I hope you come away with this video saying, okay, I know when to use the t distribution. It's when the standard deviation of the population is not given to me. When the standard deviation of the population is not given to me, I can use the standard deviation from the sample, and that'll be a fine stand-in. I'll just have to use the t-table. The one exception to this is when you're dealing with proportions. When you're dealing with proportions, as long as your sample size is fairly sizable, you can go ahead and you're going to use the z table pretty much every time when you're dealing with proportions. Other than that, you just swap out z table for t table for z table. When you don't know the standard deviation, you have to estimate it.